Specific latent heat. Latent heat means hidden heat, by which we mean that there is no temperature indication that heat is being lost or gained by substance. The specific latent heat happens in the phase change. In the graph is a blue section. Specific latent heat is defined in this formula. Q equals to ml. Q is thermal energy, m is mass, L is a specific latent heat. Since no temperature change during phase change, there is no delta T in our formula. The unit is joule per kilogram. So use Q equals to ml during phase change when delta T is equals to 0. For example, melting or boiling, or condensation or freezing. Use Q equal to mc delta T otherwise when delta T is not equal to 0. Since there are two phase change, each substance has two latent heats. One is a LF, is a latent heat of fusion, and LV, the latent heat of vaporization. Compare boiling and evaporation. Boiling takes place within the whole liquid at the same temperature, called the boiling point. Evaporation occurs only at the surface of the liquid and can occur at any temperature. Evaporation can be enhanced by increasing the surface area, warming up the liquid, or having a movement like a wind at the surface. Boiling and evaporation both remove the same amount of heat energy from the liquid. This is why sweating removes excess body heat so well. Calculating energies involving specific latent heat. Let's take a look at the example. Bob has designed 525 kilogram ice chair. How much heat must be removed from water at 0 degrees Celsius to make the ice chair also at 0 degrees Celsius? And specific latent heat of fusion is given 3.33 times 10 to 5 joule per kilogram. In a phase change, delta T equals to 0, so we have Q equals to ml. Since the phase change is freezing, we use a latent heat of fusion. So we have Q equals to ml, mass is 525, and specific latent heat of fusion is 3.33 times 10 to 5. We get 175 times 10 to 6 joule. Bob can now chill in his new chair. 3.1 Thermal concepts. Now we can discuss conduction, convection, and thermal radiation. Thermal energy can be transferred from warmer mass to a cooler mass by three means: conduction, convection, and radiation. This energy transfer is called heating and cooling. Only thermal radiation transfer heat without any physical medium such as solid, liquid, or gas. Examples: the heat from the wood burning stove can be felt from all the way across the room because photons carrying infrared radiation energy can travel through empty space. When these photons strike you, they are absorbed as heat. This process of thermal energy transfer is called thermal radiation. We're going to discuss this in more detail in topic 8.2 later. Thermal radiation doesn't need a medium. It can transfer in vacuum. Conduction. When two solids of different temperatures touch, thermal energy is transferred from the hotter object to cooler object through a process called conduction. When atoms of one portion of material are in contact with vibrating atoms of another portion, for example, so vibration is transferred from atom to atom. High T portion vibrate more than the low temperature portion, so we can imagine the vibrating impulse to travel through a material from high temperature to low temperature, and eventually the object reach thermal equilibrium. Now let's take a look at the convection. Another form of heat transfer is called convection. Convection requires a fluid as medium of heat transfer. Convection requires fluids like liquid or gas as a medium of heat transfer. For example, a hot air is less dense than cold air, so it rises. As it rises, it cools and so becomes denser and sinks. We thus obtain a cycle which forms a circulation called a convection current. First example, atmospheric convection, thunderheads. Hot air rise, cool air falls, setting up a convection current. Atmospheric convection, nuclear detonation. Hot air rises, cool air falls, setting up a convection current. Solar convection, sunspots and flares. Plate tectonics convection. This is probably the most interesting example. The residual heat from the formation of Earth and the heat generated by radioactive decay deep within the mantle combine to produce a perfect condition for convection currents. Even though the mantle acts similar to solid in many ways, it's really a special kind of fluid that would be liquid like lava if it weren't for a tremendous pressure it is under due to overlaying layers. The mantle closer to outer core heated up and rises. As it cools, it falls and sets up a convection current. It is this convection current in the mantle that drives plate tectonics. This is a perfect example for convection, as a hot mantle close to the core rises. As it cools, it sets up a convection current. Spreading centers are usually located in the ocean and produce a landform called oceanic ridges. Oceanic ridges form because as oceanic plates separate like this, magma can well up into void. Mountain created by the buckling crust can form, as well as volcanoes powered by melting crustal material. Two land plates collide and forming mountain.